I'm taking notes, so I should be okay.
Thank you.
Angela, do you actually have a YouTube channel?
I do have a YouTube channel.
So if you can, but it's a published one or it's a private one?
I have two. One is private and one is public.
If you wouldn't mind putting it up to the YouTube channel for the other students, and then we can put the link into the Canvas site, if you don't mind.
Yeah, I don't mind. I'll do that.
Okay, thank you.
Thank you.
Thank you.
Okay, what do we see here? So of course we would have the limit as h goes to 0.
Mm-hmm.
Limit h to 0. Now this is not the definition of a derivative, but this is equal to f prime of x if f of x is differentiable. If capital F is differentiable. If it's if it's differentiable, you can compute the derivative like this. But we know that if f of f is lowercase f is a continuous function, we know that this expression is actually, I wanted to do that in red, this is differentiable if f is continuous. That's the fundamental theorem of calculus, or one version of it.
Okay.
So that's where the differentiation comes in.
Ah, okay.
Right?
Yes.
This theorem 1.3 is the extension of the fundamental theorem of calculus to
RD?
To not just to RD, yes, but to integrable functions. And RD, where D is greater than 1. Because in higher dimension, we really don't have a fundamental theorem of calculus. We have sort of an equivalent of it for nice function in Stokes' theorem.
Okay.
But the other version of the fundamental theorem of calculus says that if f is equal to capital F prime, then the integral from a to b of f, lowercase f. Utah! Sorry.
That's okay, no problem, Professor. It wakes me up.
Right. This is f of b minus a, but we have to look at this a little differently, to look at this generally. So it says the integral of a function over the interval can be expressed by a function whose derivative is equal to lowercase f on the boundary of the interval. And a similar thing is the integral, if you have some set O of the divergence of some vector value functions f of x dx, O in Rd, is equal to the integral over the boundary of O of the function itself. So here you have the same dynamics. You have the integral over a derivative over the entire set can be expressed by its values on the boundary. Except that the subset O of Rd, the boundary is not just 2 points, the boundary is, you know, a whole manifold.
Yes.
So this is really another version of the fundamental theorem of calculus in Rd, but of course it requires F to be really nice. So there's two extensions. Theorem 1.3 is the extension of the fundamental theorem of calculus to really ugly functions in as many dimensions as you want. This is a special case where you extend it to really nice functions.
Professor, when you're saying nice functions, are we talking about functions that are integrable or
no, differentiable?
Okay.
Continuous and differentiable in some sense.
In the integral, the second one, what does it say under the arrow after the D?
That's supposed to be a lowercase omega.
Oh, okay.
That's the surface measure on O, on the boundary of O. But this is the content of 550, and so we're not going to do it here.
Yes. I should know it like as if I'm reading my palm.
Okay, so that's why it's called the differentiation theorem.
Yes, sir.
Okay, more questions.
After the end of the proof on page 105.
Yeah.
Second line says that the maximal function is greater than the absolute value of f.
Yeah.
So they say it's an immediate consequence, and could you help me to see why is it immediate?
Okay. Did I tell you the story of Hardy? The Hardy of the Hardy of the Hardy-Littlewood maximal function.
Yeah, you told me that. Yeah.
Yeah, well, he has this whole thing with Ramanujan and the negative 112s, but he gave a lecture once, and he said, in the proof from such and such, it obviously follows that such and such. And the student had really stared at him for a while and said, I don't see that it's obvious. And he says, of course it's obvious, because he looks at it for about 5 minutes in the lecture. Then he storms out of the lecture and comes back 45 minutes later with a stack of 20 pages of paper and said, I told you it's obvious, and here's the proof. Okay, but this sentence really is obvious, because we just have to look at the definition. We know that f of x is the limit as the measure of b goes to 0 on x in b of the integral over b absolute value f of y dy, right? And this is certainly less than or equal to the supremum of right? Because the supremum is always bigger than the limit, or at least as big as the limit, and this is equal to the maximal function.
Yes, yes. Ah.
So this one is actually an immediate consequence.
Yes, yes, it is. Okay. Next question is on the locally integrable.
Yes.
So they have these two examples, e to the x and then the 1 over square root of x, absolute value. So what about interval -1 to 1? It's not integrable.
1 over the square root of the absolute value x?
Yes. On the interval -1 to 1?
Yeah, of course it's integrable.
It is.
What is it?
Oh, square root, 1 over, yes.
1 over square root of absolute value fx dx. This is
twice of 0 to 1?
Twice the integral from 0 to 1. 1 over the square root of x dx. And this is 4 times the square root of x between 0 and 1, which is 4.
Ah, I see. It's integrable.
It's very integrable.
It is integrable. I see, no problem.
Yeah, well, but the reason is most of the functions which we live with in this day and age are really not integrable in the L1 sense. If you look at sine of x, you know, the integral of r of sine of x dx does not exist. Right?
Right.
Because you have to be able to integrate over the whole space. So therefore, it makes sense to find this class of L1 log of RD, which means it's integrable
in that small
for every ball.
Yes, small neighborhood.
And the other reason is because theorem 1.3 really doesn't require to know what the function does as the absolute value of x goes to infinity.
Okay.
And the proof of theorem 1.3 is actually, or 1.2 is actually pretty nice because it makes a nice use of the maximal function and Chebyshev's inequality. Does this answer the question?
Yes, thank you, Professor.
Yeah. Any other questions?
On the page 106.
Yeah.
Could you kind of go over the definition of Lebesgue density? So what it really mean to have certain density, or is density like a set of functions, or?
No. Okay, I'm gonna use a new whiteboard for that. I found how to get infinitely many whiteboards now. So the definition is just similar. That x is a point of Lebesgue density if the limit x in the measure of b goes to 0 of the measure of b intersected e over the measure of the ball is equal to 1. That tells you that if B is sufficiently small, then B is almost a subset of E. Right? Since the measure of B intersected E and the measure of B are very close to the same value. This is
so Lebesgue density of a set E is collection of points where that ratio goes to 1.
where that ratio goes to 1, and that means the ball is almost contained in E. It's not completely, doesn't have to be completely contained. So if E is open, then every X, for all X in E, X is a point of density, a point of Lebesgue density. And this is because if X is in E, E is an open set, then there exists a ball about X which is entirely contained in E. And that means M of B intersected E divided is the same as M of B, and so the ratio is 1 without even going to a limit. So in this way, X is of Lebesgue density is a weak version of X is an interior point.
Okay.
If you look at the Cantor set, well, we added. For the Cantor set, if X is in the Cantor set, in the regular Cantor set, then X is not of Lebesgue density. No points in the Cantor set is of Lebesgue density.
Oh.
Because M of B intersected the Cantor set over M of B
0
is always 0. Because the Cantor set is a set of measure 0. And
I see.
so what it essentially says that if B is small enough, everyone done reading this whiteboard?
Yeah, it's okay.
If B is small enough and alpha is just slightly less than 1, then there exists a ball B such that the measure of M of E, the measure of E intersected B is greater than or equal to L. So Wait.
Yes, that's right.
For any alpha less than 1, that this is the case.
Mhm. Okay.
And then corollary.
1.5, so 2 is not the negation. So it's actually more broad than, it's like, whatchamacallit? I'm not good with logic.
Almost every x not in E is not a point of density in E, of E. And it says almost every x in E is a point of density of E. It follows, if you apply theorem 1.4 to the characteristic function of E, then you see that the limit measure of B goes to 0, x in B of 1 over the measure of B, integral over B, characteristic function of E,
Mhm.
and this is the limit measure of B to 0 1 over the measure of B times the integral. Well, the characteristic function is 1 if x is in E and B, so we can integrate over E intersected B.
Mhm.
And this is exactly this.
Mhm.
Measure of E intersected B
Over.
over the measure of B.
Mhm.
And theorem,
Your definition.
yeah,
Mhm.
theorem 1.4 says this is equal to f of x for almost all x.
Mhm.
And that means it is equal to 1 for almost all x in E, and it's equal to 0 for almost all x not in E,
Mm.
right?
Yes.
And that means for almost all x in E, x is a point of Lebesgue density, and for almost all x not in E, x is not a point of Lebesgue density.
Ah, I see.
Now, but I want to say something else about this Lebesgue density thing.
Oh, Professor, I have one more question.
Yeah.
So, in the definition of the limit, x
Yeah.
has to be in the ball.
Yeah, it doesn't have to be the center.
Ah, I see. So x has to be.
In my first example, with the fundamental theorem of calculus, I made it the center. But you can make it. You could have done this example also as x minus epsilon and x minus epsilon plus 2h, and you take the limit as h goes to 0. Then it's not the center, and you will get the same result.
Yeah. Okay. Actually, I was going to ask you about the center, but you answered it.
Yeah. No, that's it's often people think it has to be the center, but it doesn't have.
Oh, okay. Fantastic.
Okay, but I want to say something else. Okay.
Mm-hmm.
if E is measurable, in our definition of measurability,
the set of f of x, oh no, it's an outer measure. There exists open set O that contains it, and then outer measure of O minus E is less than epsilon.
right?
Yeah.
But essentially, there exists an open set which is almost the same as E, right?
Yes.
And every point X in this open set, so such that M minus O minus E is less than epsilon, right? For F is an interior point of O, right? So there exists a ball about X such that the ball, X is in the ball, which is entirely contained in O, right? That's for every X in O. There exists such a ball. And that means if you look at B intersected E,
then you get B, because B is subset of E.
No, it's not. You don't get B. But the thing is, the measure of the ball okay, let me try this again. The measure of the ball intersected E complement, since the ball is entirely in O, B intersected E complement is in O minus E, right? And that would be less than epsilon. And that tells you that the number that essentially a point of Lebesgue density is almost an interior point.
Okay.
So again, this is the Lebesgue density is a weak version of interior point. And when I see weak version, I mean that's something which happens almost everywhere.
So X, element X, which is X as an element of E, is Lebesgue density. Then it's a weak version of interior point of E.
Yeah.
Okay.
Because E might not be open, right? Might not have any interior points.
Ah, okay.
Okay. More questions?
Okay, 1 second. Okay, so
does somebody else also have questions?
No.
I have a question on the page 106.
Still on 106, yep.
So they say, at this stage, two simple observations about this definition are in order. First one is okay. Second one, if X bar is in the Lebesgue set of F, then that is equal to that. Why?
Why is that the case? Another one of those obvious facts.
Okay, great.
Okay. If you look at, I leave out the limit. If you look at 1 over the measure of the ball, integral of the ball, f of y dy, oops, minus f of x, right? We do the limit later. This is 1 over the measure of the ball. And here comes the magic. F of y
Minus f of x.
minus f of x
Whole thing.
dy. And that's less than or equal 1 over the measure of the ball.
Which is positive always.
Right. And absolute value f of y minus f of x by the triangle inequality.
Yes, sir.
And okay, now take limits on both sides and you're done, right?
Limit.
This is the nice thing. If you have integral over the ball, 1 over the measure of the ball, if you normalize the integral by the measure of the set, then you can just pull in a constant under the integral and not even think about it.
Oh, but on the right hand side, we get f of x bar, not f of x.
Oh yeah, I didn't bother about the bar.
Okay.
If you want a bar, if you want a bar there, yeah. I don't know why we put the bar there. Actually.
Oh, so to differentiate any element of E from Lebesgue set of F.
Yeah.
Can I ask a question?
Yeah.
Okay, for corollary 1.6 in the proof, when it says for each rational R there exists a set ER, is that set, is it the same as page 104, like where they have E alpha? Is it the same definition but with ER instead?
No, it's not.
Okay.
Okay, the thing is, what you actually do is you apply theorem 1.4, in the first one, you apply theorem 1.4 to the function f minus r, right? And 1.4 says that this equality holds for the limit for almost every x. So this inequality holds for almost every x. So the set of x for which it doesn't hold, this is by definition the ER.
Okay.
Right? ER is the set of x. Let me write that down. ER is the set of all x in RD such that limit one over the measure of B integral over B f of y minus r dy is not equal to f of x minus r, right? This is the definition of this set, and this set has measure 0 by theorem 1.4.
Professor, on the page 107,
Yeah.
There's an inequality.
There's just one. Yeah.
There are three inequalities, but then the second one in the middle.
The measure, the integral 1 over mb integral absolute value fy minus fx bar is less than or equal.
Yeah, that one.
That's the oldest trick in mathematics.
Add and subtract, right?
Add and subtract r, and then triangle inequality.
So my question is that the second term, 1 over m of b, integral f of y minus r dy. Why is it less than epsilon?
Which one? The second term?
Yes, the first term of the right inequality.
This one?
Which one?
This term. I'm gonna write it down.
Ah, okay, sure.
B f of y minus r
dy. Yeah, that term.
That term.
Yes.
Why is that less than epsilon?
Mm-hmm.
Because
is it the definition of the limit?
it has to do with the definition of the limit.
Ah, okay, sure.
It has to do with the definition of the limit. The limit of this is, this goes to f of x bar minus r, which is less than epsilon, right?
Mm-hmm, mm-hmm.
And that is essentially the Dirichlet approximation theorem. You have a real number, and then there's a rational number which is approximated by less than epsilon.
Mm-hmm.
And this one is because if B has sufficiently small measure, then this one is close to f of x bar minus r by theorem 1.4. And since this is less than epsilon, then this should be less than epsilon 2.
Mm-hmm.
And you make this less than epsilon over 2, then you can see that if measure of B sufficiently small.
Professor, why do we utilize the rational number r here?
Because we have to put an index on ER, which is countable.
Ah.
Right? We want to, because E, the set of all points where this is not the case, is the union over all R of ER. And the only way that we can say something about the measure of this union is if it's a countable union. That's just by the way measure theory is set up.
I see, I see. Yeah, yep. I see now.
Okay, more questions?
On the same page, this theory of differentiation developed so far uses averages over balls.
Yeah.
So the averages over balls is like the 1 over measure of B. Is it
right?
Okay. So I was looking at. Okay. Yeah. So rest of it is okay. Yeah.
Yeah. So the problem is
Problem number 6, Professor.
Masood, again?
Number 6 in the...
Okay, number 6 we forget about.
Oh.
Thank you.
because it refers to lemma 3.5, which is number 6 is one of those problems which is snuck in early into the exercise section, but refers to basically the last section in the chapter. So,
oh, we are supposed to look at number 8 actually.
8?
Yes. Page 147. Page 147. Which is used in the
density.
Yes. Should we do it over the weekend and then ask you a question on Monday?
Yeah.
Yes,
I'm gonna ask you to do it over the weekend because I have myself not looked much on it.
Ah, sure, no problem.
I want to just put one more remark. They say it doesn't really matter whether you use balls or cubes or something, as long as they shrink regularly to X bar, as long as the sets have bounded eccentricity. If you look at the set which looks like this, which is really elongated, and your point X is here, right? And if you look at sets which are all of those shapes, they don't shrink nicely to X, right? And for more general sets, X in S, limit measure of S to 0. If you go for more general sets, f of y dy, this is still an open question. Right?
If you use not symmetric shapes?
If you don't use as long as you use cubes, or you can nicely bound the set by a ball of finite measure, but you could have a set like this, X is here, and you could have some awful looking set. How about something like this, where X is right here at the cusp, or something like that. So it's that's why balls and cubes are okay. Rectangles is still an open question, or at least much more difficult. It actually says up there, rectangles, the weak type inequality fails, and see problem number 8. Okay, let's see what we're gonna do for Monday. I actually do have some problems assigned. Okay. First of all, and this is actually relatively light reading now compared with this. So read section 2.
Good kernel.
Which is the good kernels. Now there's a word of warning. You may be familiar with the term kernel from algebra. like the kernel of a isomorphism or homomorphism.
Oh yeah.
Or the
This is
kernel
not the kernel.
This is a different kernel. It's entirely different animal, except that it has to do with linear mappings. So, but the kernel of a linear map in the linear algebra sense is a vector space. It's, or more generally, it's a set. The kernel in the good kernel sense is really a function, or better, a family of functions. And then there's lots of good problems about good kernels. I'm gonna ask you to look at exercises 1, 2, 3, and 8. Now both 3 and 8 are about Lebesgue density.
1, 2, 3, and 8, Professor?
Yeah. And these Lebesgue density problems are somewhat tricky. 1 and 2 is really just calculus, or very closely related to calculus.
What kind of calculus is the matter of importance?
Well, I mean, it's
Princeton calculus.
yeah, it's
should be okay. Yeah.
Yeah, the 1 and 2 are okay.
Okay.
Okay. Any last minute questions?
So Professor, your plan for the stay-at-home order is lifted on May 15th. What would be the first thing that you would enjoy?
If the who wants to set the stay-at-home, or who says I'm staying at home?
Are you in some Hawaiian resort or something?
Well, I could be. No, if I have a chance, I take my dog for a hike in the mountains.
Ah, yes.
And as long as I go into an area where nobody is, so I stay away from everyone, but I'm not really staying at home.
I see.
You know, going in the supermarket is scary. That's, but we invented Amazon, right?
Yes.
Right.
Perfect timing. Yes.
Yeah. Well, think about it. If we would have been in this situation 20 years ago.
Oh yeah, it would be horrible. No internet. Yeah, people were saying about like, yeah, no internet, no delivery, nothing.
I know someone whose internet broke down 3 days ago.
Oh. In your neighborhood?
Not my neighborhood. He's in West Hollywood, I think.
Ah, I see. Those Spectrum guys, they mess up.
Well, I'm Spectrum too, but it hasn't broken down yet.
Thank goodness. They don't. When you call the number, they don't know actually. They say everything is fine, and then like, oh my internet's not working.
Yeah, but if you think about it, if we would have been in this situation 20 years ago, the semester would have been over. And
sorry, Professor.
That would have been it, because we really couldn't have done it. But now this is really easy compared to what it would have been then. As long as the internet doesn't break down.
Professor, actually 20 years ago, we would fax it to you. We write all our questions neatly We go to Kinko's and then fax it to you, and then you pick it up.
I know 20 years ago we had telephones with conference calls already 20 years ago. So everything could have been done in audio and then with faxes back and forth, right?
Right.
That well, we could have even done it. We had email 20 years ago.
Yes, that's true too.
Yeah.
Except that if we scan something and then send it to you, it probably take 30 minutes.
The scan, yeah, with a telephone hookup, right?
Yes, I do have a question.
Yeah.
Are we having the take-home midterm 2 on the date of the final or in the last meeting?
I'm gonna put it up. When is the date of the final anyway? When is the semester over? Hopefully soon.
Over in 3 weeks.
We have 3 more weeks?
Yes. 3 more weeks of instruction.
3 more weeks of instruction. So I'm gonna post it my target date is 2 weeks from next Monday, which is like the first Monday in May, I think.
Yeah, May 4th.
May 4th. I'll post it May 4th and give you until the date of the final, which was May 9th, or when was the date of the final?
Let me confirm. Sorry, I need to pull it up. It's supposed to be on May 11th.
May 11th. Yeah. So I'll make it due on May 11th.
Awesome. Thank you so much, Professor.
Yeah. Okay, I'm gonna get rid of this whiteboard now. Thanks for recording.
Thank you so much, Professor.
Thank you, Professor.
Yeah.
Have a good weekend, Professor.
Yeah.